Okay, this is going to be a quick introduction to slope fields. And I know this is a calculus topic, but we're going to go back to Algebra 1 for a minute. And we are going to make a good old t-table. So just as we did in Algebra 1, we're going to pick some x values. And I'm just going to pick some nice values to work with. Usually we like those whole numbers, although you would not have to pick those, or integer values. And then I'm just going to plug them into my equation that I have here. So I have an equation that I'm given, dy dx equals 2x. So supposing I plug in a -3 there, then I would get dy dx equals 2 times -3, which is -6. 2 times -2, which is -4, and you get the idea. We're going to get a -2 here, 0, a +2, a +4, and a +6, and that was me plugging into this equation, plugging my input in and getting an output. Now, the only difference is when we get an output, our output in algebra is usually a y value, so we end up with coordinate points. What I mean by that is if we look at any one of these, that represents a location on my graph, 1, 2, which would be right here. But that's not the case here because the output is dy dx. So here's where we need our calculus knowledge. Dy dx represents slope, that's right. So what we actually are figuring out at the point that I'm just kind of starting with here is that at x equals 1, the slope is 2. So we could go ahead and we could pick whatever x value we want. So let's go ahead and stick with that point that I've labeled. That's 1, 2. I just need an x value of 1, so 1, 2 certainly works. At that point, I want to do a slope of 2. So I'm going to draw a little kind of slope line here. I'm visualizing that if I were to go up 2 and over 1, that would be my slope of 2, but I'm just going to draw a little kind of portion of that. And then I'm going to check and see if there's any other points where the x value is 1. And hopefully you're saying, yeah, sure there is. There's an x is 1 here. That's 1, 0. That's 1, -1. That's 1, -2. That's 1, -4. That's 1, 5. And it turns out all of the points in that column are all points that have an x value of 1. So at each one of those, I want to draw a little slope line that has a slope of 2. So they're parallel little slope lines. We could think of it as when we're drawing those little kind of tangent lines in, that's what this is resemblant of. Okay, so let's pick another one. Now let's go ahead and do, 2, 4. So I'm going to go over here at x equals 2, 0, and I'm going to draw a slope of 4. I'm trying to visualize, and for the perfectionists out there, you just got to let go. We're just trying to visualize if we would go up 4 and over 1, what would that look like? So definitely steeper than my 2, and that means this is going to be 4, and that's going to be 4, and that's going to be 4, because all of these points in this column have an x value of 2. And let's do this last one. If x equals 3, now I need a slope of 6, and it gets kind of tough, guys. So basically, I'm just going to try to make it steeper than my 4. It's like almost looking like it's a vertical line. Not quite, but slope of 6 is pretty steep, up 6 over 1. Okay, it gets a little bit easier if we go 0, 0, because we can all graph a slope of 0. So at x equals 0, my slope is 0, and you're getting the idea of what's going to happen here. At -1, my slope is -2, so now I'm going to reverse what I did. And all of these x values, again, I'm doing a column because my x value is -1 in every point where I just graphed that slope. Those got a little messy at the end. Be a little more careful here. Good news, you'll never be asked to do this many, but I want us to actually see the picture. So in a second here, I'm going to ask you, what are you noticing? Putting in my slope of -4 here, whenever x is -2. And then when x is -3, I need a slope of -6, and those are my real steep ones over here. And obviously, I'm not going past that. You could, but it's going to get hard to even graph. And I want you to just observe that and see, what are you seeing when you look at that slope field? Because what the slope field is giving us is it's giving us a picture of what the solution looks like to the differential equation. That was a lot of words. This is a differential equation, an equation with a derivative in it. And the solution is a function such that its derivative is the differential equation. So hopefully you're seeing a parabola, and that should make sense because the equation whose derivative is 2x, well, isn't that just x squared? Or should we say x squared plus a constant? And if we take the derivative of that, we end up back to here. That's exactly what we've been doing because we've been finding the integral of functions or the antiderivative. So that should make a lot of sense. The new part is, oh, we're actually picturing these. And at any point, you could sort of picture one of these. I'm going to pick out this point that I had right here, and I could say that I could kind of like draw. You're not necessarily going to pass through every point. You might go between slopes, but at any point in your slope field, you should be parallel to the slopes that you're passing through, kind of the area. Because remember, we could also do slopes. We could have picked 1/2 and put that in our table. So it's not going to be all-inclusive and perfect that you're going to have every point, or have a slope at every point that you pass through. So I drew one particular solution that would be dependent. We would need the slope field itself shows us all of the general solutions, which would be the family of functions shifted up or down with that plus c. The particular solution would be if I give you just one point, and the point that I just happened to look at here was 1, 2. If I give you just one point, you could trace, you could find an equation of that particular parabola. So we're going to do more with the solving differential equations, getting to the equation, but right now we are just picturing those solutions via slope fields. I'm going to skip 2 and let you go back to that. Let's do number 3 because there's something interesting happening in number 3, and I'm actually going to let you go ahead and pause the video if you want and work through it. I'm going to start you off, but you can certainly sort of go off on your own here in terms of you got the idea and run with it. Two divided by 0 is undefined. 2 divided by 1 is positive 2. 2 divided by positive 2 is 1. And 2 divided by 3. Just write that as 2/3. So we've got some interesting slopes to graph here. But what I really want to point out here before we get too far into this is that in this particular one, because my differential equation is in terms of y, these are y values and not x values. So if I'm reading this, again, I'm just going to pick one to start with. I actually really like starting with slopes of 1. My slopes are 1, my dy dx is 1, for every spot where y is 2. So I'm trying to find a point where y is 2. That would be right here, 0, 2. 1, 2, 2, 2, 3, 2, 4, 2, negative 2, 2. Negative 4, 2. And if you notice, all of my points that I just selected are in a horizontal line. Well, that makes sense. The y value always has to be 2. So I'm trying to sketch a slope of 1, and that's just going to be a diagonal on this graph, straight diagonal. Whenever my y value is 2. So notice, compare that to the first one we did, and now all of my slopes are in a row. All my slopes in a row are the same versus the slopes in a column being the same. So I'm going to reverse that, and I think the next one I'm going to do is this one. At negative 2, my slope is negative 1, and that just feels like that would be not too bad to put in there. At 1, my slope is positive 2, so a little bit steeper. Again, I'm visualizing up 2 over 1 versus this was just up 1 over 1. Okay, hopefully this is going to work. I'm not sure if it's going to pick up where I left off, but I just wanted to save a little time there, and I finished filling in my slopes that I had. So just a quick talk through. Something like this one here was a slope of 2/3 because I'm at y equals 3 up to over 3. So I tried to draw a little slope that looks like that. And then we have, of course, our vertical lines for our undefined slope. And you are encouraged to kind of think about what does that look like. And hopefully you're coming up with something like a sideways parabola is a good thing to be seeing here. And that is not y equals x squared, that is x equals y squared. So that's an interesting one because the other one was pretty intuitive, that the derivative of y equals x squared gives us 2x. And I'm not sure how the derivative of x equals y squared gives me 2 over y. So that is going to be our challenge for our next time that we're together, is to figure that out. But for now, we are visualizing what the solution, what the function is that would have that derivative, or would have its slopes described by the equation dy dx equals 2 over y. Okay, if this video is still working, number 5, I'm going to skip. 4 you're going to do. You should be just fine with that. Number 5, there's a video that Sal Khan has done, which is excellent. So I'm not going to redo that one. I'm going to do number 6 and tackle that one with you. So let's go ahead and flip it over. You might want to pause and do number 5 first. 6 will be a little bit more challenging than 5, but they're similar to each other in terms of they're both in terms of x and y. So now instead of just having an x or just having a y there, I've got to deal with both. So how are we going to do this? Well, we're going to just pick some points. So let's pick some points. I don't know. Let's do 1 and 1. If x is 1 and y is 1, then my slope is 2, because I'm just adding them together. And that makes me think, what if x was 1 and y was -1? Well, then I add them together and I get 0. Ooh, that's interesting. Zeros are always interesting. Look for zeros. If x is 2 and y is 2, then I get a slope of 4. I'm not seeing a pattern there other than whatever my x, if my x and y are the same, then I double it for the slope. But I am seeing a pattern that if I have 2 and -2, then I have a slope of 0 again. If I have -2 and +2, I have a slope of 0. When x and y have opposite signs, then the slope is 0. And I'm actually going to start by trying to graph that when x and y have opposite signs. So that would be, and let's just find those. 1, -1 is right here. 2, -2, 3, -3, -2, +2, -1, +1. So that's like my negative diagonal. Zero plus 0 is 0, so we'll add that in there. And okay, what else do I have? 2. At 1, 1, my slope is 2. At 2, 2, my slope was 4. That got steeper. I'm just going to do a few in here, and I think that's going to try to help us. So now I'm just going to talk through a couple. 1, 0, well, 1 plus 0, my slope is 1 right here. And 2, 0, my slope is 2. And I think what I just figured out, I just figured out something just by even talking through that. If I go 2, -1, my slope is 1 because 2 minus 1 is 1. And what I'm figuring out here that I just kind of happened upon is that sort of following this same diagonal here, right next to my other diagonal, if my, how can I phrase this? If my x value is always 1 bigger than my y value, and they're opposite signs, I'm going to get a slope of 1. So I had 1, 0, 2, -1. Now if I go 3, -2, 3 minus 2 is 1, 4, -3, and I'm getting slopes of 1 all along here. Let's do a quick check. -1, +2, -1 plus 2, that's a 1. So then to get a -1, well, I'm going to need to have my y value be 1 more than my x, but be negative, or whichever one's negative to be 1 more. So instead of being 2, 1, for instance, or 2, negative 1, I need to be 1, negative 2. 1 minus 2 is negative 1. So I'm going to go at 1, negative 2 and find a slope of negative 1. And then I'm going to go at 2, negative 3. 2 minus 3 is negative 1. 3, negative 4, negative 1. And I'm going to get this other diagonal. Let's check. Negative 3, positive 2. There it is, negative 1. So there are definitely some patterns here, but this one is a tough one to see in terms of patterns. And I haven't realized actually until I was just doing this that I think maybe we can keep making diagonals of patterns. I'm going to play around with this next kind of diagonal here because I started to do that and I'm thinking that we're always going to have a slope of 2. So let's see, if we had 1, 1, we had a slope of 2. If we have 2, 0, we have a slope of 2. If we have 3, negative 1, slope of 2, because I'm adding these. 4 minus 2 is a slope of 2. So yeah, sure enough, we're going to have a slope of 2 for every diagonal here. And then I'm maybe going to have a slope of 3. I'm just guessing. If I go right here, 2, or positive 1, positive 2, slope of 3 when I add them. Positive 2, positive 1, slope of 3 if I add them. 3, 0, there it is, slope of 3. Slope of 3, slope of 3. Cool, guys, I just figured something out. I did not know that it worked that way. And then I've got slopes of 4. I feel like I want to change color here. Slope of 4 for this diagonal. And you get the idea. So let's go maybe one more in the other direction. One more in this direction. If I'm at negative 1, that would be negative 2. Negative 0, negative 2 would be negative 2. 1, negative 3 would be negative 2. This one gets a little bit harder to see, so as far as seeing the solution, but you will be able to see that there's sort of a weird kind of curve going on here, almost like we go here and then like curve, and there's your family of functions. So these will be a little bit more of a challenge for sure, but I think you guys have the idea of it. So you've got some to try and play around with. I encourage you, if you can try to recognize a function, do it. This one is not one that I'm recognizing, and actually I'm going to tell you this is one that we're not going to be able to solve using a different method. So this is one where the only way we might be able to, at least at this point in our mathematical career, be able to picture this differential equation, the solution to this differential equation, is actually by making a slope field. So it is going to be a tedious method, but it is going to allow us to picture any differential equation, even the ones that we get stuck on using some of the other methods we'll look at. Okay? So hopefully you found that helpful. Good luck with the rest of your slope fields, and I look forward to continuing to work with you on them.